Let's look at the very last example of section 1.7, the chain rule. Example 4 is saying the position of a particle moving along a coordinate line is s equals square root of 69 plus 4t with s in meters and t in seconds. So I'm going to have a particle. Let's take a little particle, and it's just moving. Sometimes it's going to the fore, going forward, going back, going forward, going back. You know, it's moving. And this equation right here will tell us where this particle is located at time t. So if they ask us to find the position, we're going to plug it in here. But is that what they're asking? Let's see. They're asking us to find the rate of change, the rate of change of the particle's position. So how fast its position is changing, its velocity. So what we need to do is, we're not only working with this position function, we need to find out how fast position is changing. So we need to find the derivative of this function. Okay, so we need to find the derivative of the position function. So let me first write s as 69 plus 4t raised to the 1/2 power. So that's the first thing that I always do. Whenever we have this square root expression, let's go ahead and write it as something, the radicand raised to the 1/2 power, so that we can apply the power rule. So here we go. Let's go ahead and find ds dt or s prime. Hold on a second. Okay, now let's find ds dt. In other words, s prime. Okay, let's find how fast this position is changing with respect to time. That is just s prime. So let's use the power rule. Bring down this half to the front, right? We're going to have 1/2 times 69 plus 4t raised to the negative 1/2 power. But don't you forget about that chain rule. Now we need to multiply this by the derivative of the inside function. And the inside function is just 69 plus 4t. So let's go ahead and write that. We're multiplying this by the derivative of the inside, which is 69 plus 4t. Okay, let's keep going. So I'll keep this the same, 1/2. 69 plus 4t to the negative 1/2 power. But now let's go ahead and figure out what derivative of 69 plus 4t is. Derivative of 69 is 0, right? And derivative of 4t is just 4. So that's simple, isn't it? That's simple. It's just going to be 4. And I get to simplify this. If you notice, there is half in front. There's a half right there. And there is 4. So if you multiply them, we're going to get 2. And let me do something. I'm going to put the 2 on top of the fraction. And we will actually put this in the denominator because it has a negative exponent, right? I can not only write this as 69 plus 4t to the 1/2 power, but notice that half is positive this time. I can just bring the square root notation back and write it as square root of 69 plus 4t. So we found ds dt or s prime. So what did they want? We found out the derivative function, and this is a function that's going to help us find the rate of change of this particle's position at any given time. They did say plug in, or they did give us that t is equal to 3. So let's go ahead and find s prime of 3. We just need to plug in 3 into this function. 2 over square root of 69 plus 4 times 3. I hope it's a perfect square, guys. 2 over square root of Let me see. I got my calculator. 69 plus 12. Well, that's, oh, hello. Look at that. That's just 81. So this is going to be 2 over 9. And let us be very careful with the unit over here. This is, and you know, they were talking about distance. So I'm going to go ahead and actually write this as a decimal. Oh, decimal's not that pretty. But, you know, approximately 0.22 repeating meters per, and t was what? Seconds, right? I still like 2 over 9 better. So you know what? Let me go ahead and get rid of the 0.22 repeating. Let's go ahead and do 2/9 of my meters per second. Let me go ahead and get rid of this s. So that's how fast, or that is the rate of change of this particle's position at t equals 3. Okay? And that is it for section 1.7. But I will go ahead and record one daily problem, because I made it into a random. I will do one so that you guys can try a similar one for the daily problem. Okay?